Well, let us discuss the normal modes in coupled vibrations. We have already discussed the case of free, forced and damped vibrations, and this is a case where the system is coupled, and we will consider, like in shown in figure, that is two bobs, which is the simplest case. Two bobs, we will take it identical case, that the bobs are exactly same masses and identical with each other, and they are coupled with a spring in between them and suspended from a rigid support. Now when you allow the system to oscillate, this oscillation is now a case of coupled oscillations. Now when we want to see the physics of such kind of motions, we must recall that in case of a oscillations, the restoring force are the prime forces which try to bring back the body into its original positions. Now when the body is under gravity, when it is oscillating under gravity, that means a bob allowed to, single bob, if you are allowed to oscillate, then it is the gravity here which brings back the body to its original position. So therefore the restoring force is minus mg sin theta, as you see in the figure 1. Now when you have a spring kind of forces such that the body is on a flat surface with, of course, the coefficient friction 0, then the spring force is responsible to bring the body back to its original position. So therefore the restoring force there in case of a spring is minus kx. So now when you tie up these two identical bobs with a spring and allow to oscillate under gravity, so the restoring forces are here two in natures, that is one due to gravity and another due to that of your spring. So when you allow the body, I mean the coupled system, to oscillate in such a manner that the displacements of each of the bobs are same, then as if in that case the spring does not play any roles, so therefore that is the case of simple harmonic oscillations. That means you can imagine that two simple harmonic oscillations identically moving together. That is the simplest case. But when the displacement of the bobs, pendulums here, are unequals, as I have shown in the figure, that is for the pendulum 1 the displacement is x1, and for pendulum 2 the displacement is x2, small x1 and small x2. If the displacements are unequal, then the cases are really the coupled cases, where the stiffness or the coupled factor will bring the changes in the equation of motions, in the corresponding modes of vibrations and in the frequencies. How? Now when the body is unequally displaced, that is the pendulums, they are moving with unequal displacements, we can write the equation of motions for pendulum A and pendulum B. For pendulum A, if you focus, the equation of motions we can write as m d square by dt square of small x1 must be equal to minus mg small x1 by L minus k times x1 minus x2. Here the restoring force for the when the bob A is considered is obviously mg sin theta, and sin theta we have replaced as by x1 by L, because if theta is the angle subtended by the vertical with that of the string, so in that case your sin theta is nothing but the displacement x1 by the L. So therefore the sin theta we have replaced it by x1 by L. And in the second kind of the restoring force, that is minus k within bracket x1 minus x2. Similarly for pendulum 2 we can write the equation of motion as m d square by dt square of small x2, which must be equal to minus mg x2 by L, and minus k times x2 minus x1. The important thing you must see here, that whenever the restoring force due to the spring force you are considering, the spring force, I mean the restoring force is owing to that of spring, have two parts. One because of the pendulum A and because of the pendulum B. Now when you consider pendulum A or the first pendulums, the restoring force is minus kx1, and simultaneously plus kx2. It is plus kx2. It is because when the pendulum A is getting a restoring force due to the spring in one direction, the other pendulum tries to pull it in the reverse directions. That means the restoring force on pendulum A and pendulum B are exactly opposite to each other. So that is how the terms you have written minus k x1 minus x2 minus k x2 minus x1, which are opposite to each other. This is the important thing you must focus in the discussions. Now when you add these two equations which you have set for pendulum 1 and pendulum 2, you can get that is m d square by dt square of sum of x1 plus x2, which must be equal to minus mg by L times x1 plus x2. And here you can always write the sum of the x1 plus x2 to be equal to capital X1, so that the equation can be rewritten as d square by dt square of capital X1 plus omega 1 square capital X1 equal to 0, where omega 1 is equal to square root of g by L and the corresponding frequency f1 must be equal to 1 by 2 pi square root of gl. Here capital X1 is we have selected as sum of the displacement small x1 plus small x2. In the same way, we can subtract the equations which we have written for pendulum A and B to write that is m d square by dt square of x1 minus x2 must be equal to minus mg by L times x1 minus x2 minus twice k x1 minus x2. Now here again, if you select that capital X2 equal to x1 minus x2, small x1 minus small x2 is equal to capital X2, then we can rewrite the equation as d square by dt square of capital X2 plus omega 2 square x2 equal to 0, where your omega 2 must be written as square root of g by L plus 2k by L, and the corresponding frequency f2 must be equal to 1 by 2 pi square root of g by L plus 2k by L. So now here these two expressions, that is we have written the linear homogeneous differential equations we have written in terms of capital X1 and capital X2, that is d square by dt square of x1 plus omega 1 square x1 square capital X1 is equal to 0, and d square by dt square capital X2 plus omega 2 square capital X2 equal to 0. These two equations are called the normal mode of vibrations. And normal mode of vibration, it is because this is the simplest case how the oscillations are possible. And if you see, you can compare this normal mode of vibrations similar to the case of simple harmonic oscillations. To remind you that the oscillations of a coupled systems are not always normal modes in nature. That means it is not essential that the coupled oscillations will always vibrate in a harmonic manner. It is not essential, but whenever it can be expressed in a harmonic formulations like the cases we have shown here, then that is the case of normal mode vibrations. And here the coordinates, that is capital X1 and capital X2, we call as normalized coordinates or normal coordinates, and the corresponding frequency f1, f2, which we have written f1 is equal to 1 by 2 pi square root of g by L, and f2 equal to 1 by 2 pi within square root g by L plus 2k by L. These frequency are the characteristics frequency of this normal mode vibrations, which is called normal frequency. Now we can see the physical situations of this problem by selecting that the displacements are equal and the displacements are exactly opposite to each other. Nevertheless, the displacements can take various values, but we will discuss only two extreme cases. That is one case where the small x1 and small x2 are exactly same. That means your capital X2, which we have taken x1 minus x2 equal to 0. So in that case, if capital X2 is equal to 0, your normal mode equation, second equation, which we have written d square by dt square of x2 capital X2 plus omega 2 square capital X2 is equal to 0, this equation completely vanishes. It is because x2 do not play any roles. Now only the equation remains is d square by dt square of capital X1 plus omega 1 square capital X1 equal to 0. This equation only describes the motions. Now in this case, what happens if the displacements are exactly same? You can now see that the bobs as if they move together. That means the three situations as I have shown in the figure, they forget the springs, as if the stiffness of the spring is totally not there. So coupling factor doesn't play any roles, and the vibrations of these pendulums are exactly in phase, and this kind of vibrations we say as a normal mode vibration 1. And here the normal frequency are same as each of the frequency of the individual pendulums. And the frequency, normal mode frequency, what is the case here is F1 is equal to 1 by square root of G by L. This is the case when the displacements of individual pendulums are exactly same. That means they move together. It's just like two pendulums independently oscillating. You can imagine just only having the spring in contact. Spring do not compressed, or if there is no rarefactions or compression of the springs. Now coming to the other extreme case, that is when displacement are exactly opposite but magnitude same. That means x1 is equal to minus x2. So in that case, your capital X1 vanishes. That means the normalized mode vibration d square by dt square of capital X1 plus omega 1 square capital X1 equal to 0. This will vanishes, as this will not have any role to play. And only left out equation is d square by dt square of capital X2 plus omega 2 square capital X2 is equal to 0. This equation will describe the motions. So in that case, the corresponding normal frequency will be F2, which equal to 1 by 2 pi square root of G by L plus 2k by ohm till 2k by m. That is called normal mode 2. We will say normal mode 2 here. And vibrations in this case, as I have shown, the springs just vibrates in opposite directions, and as if the spring uses the best of its stiffness, the maximum of the stiffness the spring can use. And here the normal frequency with which the system is vibrating up is always more than the natural frequency of independent vibrations of the individual pendulum A and B. And this is a case, these two cases are the two extreme cases of the normal mode vibrations. But however, in between a large number of possibilities are there with which the system can oscillate. You can have like this, so many cases there is possibilities are there, and we have discussed the maximum, the two extreme cases. Now we will check that why we have selected the pendulums are identical. It is because the pendulums, when they are exactly identical, having same masses, that is m1 equal to m2, that is the total exchange of energy conditions under which the system can exchange the energy in total. We can check this one by looking to the solution of the normal mode equations, that if you see to the normal mode equation d square by dt square of capital X1 plus omega 1 square capital X1 equal to 0, the solution of this is similar to that of your SHL, simple harmonic oscillations, which is sine or cosine terms. Now here we will select the cosine terms. You can try yourself for sine terms also. We will select here cosine terms. So we can write the solution of capital X1 to be equal to capital X1 is equal to capital X10 cos omega 1t plus phi 1. And similarly, the solution for the other normal mode equation d square by dt square of capital X2 plus omega 2 square x2 capital X2 equal to 0. This solution we can write as capital X2 will be equal to capital X20 cos omega 2 t plus phi 2, where the capital X10 and capital X20 are the amplitudes or the amplitudes of the normal vibrations. When the body is vibrating in normal mode 1, that is the vibrations amplitude, and X10 and X20 is the amplitude in normal mode vibration 2. Now here we will try to go for one substitution here, that is capital X10 must be equal to capital X20 equal to twice of A. The substitution here, why we are choosing it is because in the latter part of the discussion we will see that these kind of substitutions will enable us to apply one of the formula of the trigonometry to express our objective into sinusoidal forms. So therefore, if you do this, substitution, that is capital X1 0 equal to capital X2 0 equal to twice A, then in that case the solution which you have written capital X1 will reduce to capital X1 is equal to twice A cos of omega 1 t and capital X2 equal to twice A cos omega 2 t, where phi 1 and phi 2 we have set to 0. That is the phase factor. For simplicity we have taken to be 0 for discussions. Now in that case, if you recall the generalized coordinates, this half of the generalized coordinates, now if you take capital X1 plus capital X2 by 2, that will give you the displacement due to the first half, as we have said. So therefore, and similarly you can check also, if you take the normalized difference of the normalized coordinates by 2, that is a capital X1 minus capital X2 by 2, that will give you the displacement to the second pendulum, that is small x2. So now therefore your small x1 can be written as half of capital X1 plus capital X2. Now already we have got the expression for capital X1 in terms of 2a cos omega 1t and capital X2 is equal to 2a cos omega 2t. So we will substitute that one here and that will give you equal to, that is small x1 equal to a times cos omega 1t plus a times capital A times cos omega 2t. So this is now similar to cos c plus cos t. We will apply that formula of cos c plus t. So therefore it will be equal to twice capital A times cos within bracket omega 2 minus omega 1 by 2 times t again into cos of within bracket omega 2 plus omega 1 by 2 times t. So now the first we will have two terms here of cosine. So we will now join the twice a cosine term, that is twice a cos omega 2 minus omega 1 by 2 into t. This term we will substitute as capital A1, which will say amplitude of the pendulum, of the first pendulum in the normal mode vibrations. That we will assign as A1 capital 1. So therefore the displacement expression for the first pendulum small x1 can be written as equal to small x1 equal to capital A1 cos of omega 1 plus omega 2 by 2 into t, and where this capital A1 is nothing but twice A, capital A of cos omega 2 minus omega 1 by 2 into t. And in the same way we can write the small x2 equal to half of capital X1 minus capital X2, which can be equal to capital A cos omega 1t minus capital A cos omega 2t. Right? Now this is a case of cos c minus t. Again we apply the formula of cos c minus t and simplify it. Then we can write small x2 equal to twice A, capital A of sine within bracket omega 2 minus omega 1 by 2 into t times sine of within bracket omega 2 plus omega 1 by 2 into t. And this first sine term, that is twice of A times sine within bracket omega 2 minus omega 1 by 2 into t. In place of this one we will write it is capital A2, which is the amplitude assigned to the pendulum 2 in this normal mode vibrations. Nevertheless, you can exchange this A1 with the second terms, that is the second, we have two terms each in sine and cosine. You can exchange always the other terms, that is plus term omega 1 plus omega 2 by 2 into t, to join with the amplitude terms, and the other terms as phase factor you can write. Now in this case, if you see to these displacement equations of the individual pendulums having the amplitude capital A1 and capital A2, the picture shows that capital A1 and capital A2, which are the amplitudes, they vary harmonically. Because why harmonically? It is omega 2 minus omega 1 by 2 into t, which is in cosine terms. So therefore in sine and cosine terms are there. So therefore there is a continuous variations. Harmonically this amplitude is increasing and decreasing, and you can check that when capital A1 is maximum, capital A2 is equal to 0. And when can your capital A1 will be maximum? That is when omega 2 minus omega 1 by 2 into t equal to 0. Then capital A1 is equal to 0, and therefore the capital A2 is maximum. So therefore capital A2 becomes 0. And in the reverse case, when omega 2 minus omega 1 by 2 into t equal to pi by 2,
the capital X1 is minimum, and in that case A2, capital A2 becomes maximum. This is again possible. So that means if A1 is equal to 0, capital A1 is equal to 0, entire energy with the second pendulum and vice versa. But when you have the mass of the pendulums are differing, that is, they are M1 not equal to M2, you will see that there is not a single instant at which either the pendulum 1 and 2 are stationary. There is no cases the pendulum in any of the pendulums they cannot be at rest. So therefore, though there is exchange of energy, the total energy of exchange of energy means entire energy of a oscillating system transferring to another body is not possible. It is only possible only when M1 equal to M2. In other cases, the total energy is not possible. Still, study the more complicated cases by increasing the number of pendulums more than 2 cases, or by increasing the number of springs more than 1, 2, 3 like that, or both. And in that case, the solutions will be easier if we will switch over from the usual methods to a matrix formulations and solve these ones. We will see more about these problems in our subsequent discussions. Thank you.